2005 E&M number 1. We're given an electric field diagram here and 4 points marked on it, A, B, C, D, and the field lines are pointing up and to the right and down and to the right, mostly to the right. So part A, at which of these points is the size, magnitude of the electric field greatest? Well, the density of electric field lines, how close they are together, is a measure of how strong the electric field is. Remember, this is just a visualization of the effects that we see. If we put a positive test charge at point D, how is it going to move? It's going to move up and to the right. The closer the electric field lines are, the stronger the electric field is. So point C, farthest along the x-axis, is where the electric field lines are the densest. So that's where the electric field is greatest. So C, E field lines closest together. Okay, now where is the potential greatest? Probably. All right, where is the electric potential greatest? Also keep in mind that the field lines also tell you that you're moving from high electric potential to lower electric potential. So they point towards a negative charge and away from a positive charge. So this would be sort of like you have a plus charge up here and a plus charge down there, and then a double minus charge. That's not an equal sign, that's a double minus charge over here. So any electric field lines coming from the plus, they go to the minus. So the positive charge is the high electric field, high voltage, and the minus is the low voltage. So where is the highest electric potential? I would probably say point A. So A, that's C. 2, that would be A, because field lines point from high potential to low potential. All right, now they're going to mess with us by having it be an electron, not a proton. And it's released from rest at point B. Let's get rid of these extra things that are just going to get in the way. Describe the electron's motion in terms of direction, speed, and acceleration. Okay, so at point B, here's our electron right there. And electrons move in the opposite direction from the electric field. And you can see that below 0.06, the field lines point up a little bit, and above they point down a little bit. So the electric field at 0.06 probably points entirely to the right, all along there. That would be our asymptote. So an electron placed there is probably going to stay at y equal to 0.06, but it's going to move in the opposite direction and it's going to accelerate. So B1 electron will accelerate to left, and just to make sure that the graders don't misunderstand you, towards point A. But the acceleration will decrease because the electric field lines are spreading out. Spread out along its path. However, the acceleration is not going to go negative. It's still going to be speeding up to the left. Will continue speeding up. So the acceleration is going to get smaller, but the speed is still going to get bigger. Sort of like if you're in a car at a red light and you push down on the accelerator, you speed up a lot initially, and then you ease up off the accelerator, but you don't put your foot on the brake. So it accelerates a lot initially, but the acceleration gets less and less and less, and eventually way down here, maybe it gets to constant speed, but there's no indication that it's going to be slowing down. Part 2. Calculate the electron's speed after it's moved through potential difference of 10 volts. Okay, so that's just a conservation of energy. We're going to have potential energy initially, so that's QV, and that will get turned into kinetic energy. Keep in mind the V on the left is voltage and the V on the right is velocity. So the velocity after a while is going to be 2QV over m, and we need to make sure that we use quantities for the electron. So there'll be 2, and then the charge on the electron, 1.6 times 10 to the minus 19th. They tell us the voltage that we're going to be using, that's 10 volts. And you can look up the mass of the electron, it's times 10 to the minus 31st kilograms. Don't forget to take the square root, and you should get a pretty big number of 1.9 times 10 to the 6th meters per second, which is still only roughly 1% of the speed of light. It's actually less than the 1% of speed of light. All right, I need to clear this out so I can have space for C and D. All right, points B and C. Okay, so B is at 0.08. C looks like it's at 0.09, both measured in meters. And they're separated by a potential difference of 20 volts. Let's get the size of the electric field. All right, so C, electric field is minus delta V over delta X, and they said magnitude. So if we do magnitude here, then we just take the positive of whatever those guys are. And they say that from B to C is 20 volts, and it's also, we go from 0.08 to 0.09. So that's going to be 20 divided by 0.01, also known as 2000, and we can measure that in volts per meter because that's volts on the top and meters on the bottom. So we have to assume that the electric field is roughly constant between there. So we're assuming assumptions. E at midpoint is the average E field between B and C. Notice how the electric field lines are getting closer and closer together. So it's at the midpoint. We don't know, is this the actual average or is it a little bit less than the average because there's less on this side, more on that side. We don't know if this is a linear change in there. So we're just assuming that the midpoint is the average, and we can do that because in this region it's roughly uniform. On the diagram, draw an equipotential that passes through point D and intersects at least 3. Okay, now remember the relationship between equipotential lines. Equipotential lines are perpendicular to electric field lines. So what we need is a curve that's going to be perpendicular to all of these electric field lines. So draw an electric field line here, electric field line here, electric field line there, electric field line there. And then we connect them to make sure that they go through point D, and you should have something that curves up like so. And we need to make sure that we indicate that we think that this thing is perpendicular to these guys.